Welcome to Module 1 of PyTorch Fundamentals. Over the next few videos, you're going to build your first models with PyTorch. Now, I'm guessing you're here for a reason. Maybe it's because PyTorch powers cutting-edge AI research, or maybe your employers are asking for it, or perhaps you've heard it's the easiest way to build deep learning models. All great reasons. But let me show you what really makes PyTorch special using an example. Now let's say I want to add two numbers and see the result. In PyTorch, here's the entire code. Now, if you haven't seen tensors before, don't worry about it. They're just PyTorch's way of storing numbers, and I'll explain more about them soon. For now, just notice how simple this is. That's it. It just looks and acts like a regular Python. And when you print the result, you'll see the actual value right here. Now, you might be thinking, so what? That just looks like normal code. Exactly. That's the point. Today, deep learning can feel like writing regular Python. But it wasn't always like this. You see, machine learning works very differently from traditional programming. To make that concrete, imagine you're building a recommendation system. Now, this is code that suggests products to customers. In traditional programming, you'd write rules. If the customer buys a camera, let's recommend some lenses. But what if it was a gift? And what if your friend already had 5 lenses? You might need thousands and thousands and thousands of rules for every single exception, and you'd probably still miss something. Now, this is where traditional programming can hit a wall. In traditional programming, you would write these rules to transform inputs to outputs. But in machine learning, you give the system examples of inputs and outputs, and it will learn the rules for you. Deep learning takes this further using neural networks. Give them customer histories, and they'll learn what people tend to buy. Show them cat photos, and they'll learn what makes a cat a cat. But here's the catch. And here's why early tools were so complicated. To learn from thousands or perhaps even millions of examples, neural networks have to do a massive amount of math. Every single example that you show it, every cat photo, every purchase history requires so many calculations across the entire network. And this can happen over and over and over, building up to millions of calculations as the network slowly learns the patterns. The early frameworks were so focused on handling all of that computational power that even the simplest things could become absurdly complex. Let's go back to wanting to add two numbers. Brace yourself. Do you want to see the result? You couldn't just print it, you get something cryptic like this. But why did deep learning tools work this way? Well, the early frameworks made a deliberate choice. They used something called a static computational graph. It's a bit like a factory assembly line. You had to define every step ahead of time in order, and then you compile it and start running data through it. If you made a mistake, you want to experiment, you forgot one operation and you need to insert it after step 2, well, you can't. The assembly line is already built and running. You have to stop everything, tear it down, redesign it, and rebuild it from scratch. And that's not all. You could not test individual parts. You had to build the entire assembly line before you could run any of it. You couldn't use normal Python if statements or loops. Instead, you had to use special operators that were complex and unintuitive. And your assembly line could only handle inputs of one fixed size. Now, imagine if Python functions only worked with lists, for example, with exactly 3 items. You couldn't even use normal Python debugging. When something went wrong, the error messages pointed to internal system code and not where you actually made the mistake. People could be spending their time fighting their tools rather than doing the actual work. So PyTorch emerged from this frustration with one core principle. Deep learning should feel like normal Python. PyTorch introduced a new way to handle computation. You just write clean Pythonic code and PyTorch takes care of the rest. You can use your normal loops, your if statements, you can change anything anytime. It all just works. And when something breaks, the error will point to your code. You can stop your program, inspect the variables, and fix problems just like anything else that's Pythonic. But PyTorch became more than just a tool. Today, it's backed by a massive community, researchers sharing code that you can reuse, solutions to common problems, and constant improvements. There's an answer to almost any question that you might have. And this mix, Python's simplicity, powerful tools, and a thriving community is why PyTorch has become the go-to choice for everyone from students to researchers at the cutting edge of AI. And now, you're ready to join them. Whether you're exploring new ideas, growing your career, or just getting more comfortable with the framework, you're in the right place. So let's get started. In the last video, you saw how neural networks learn. starting with our delivery time problem, where a single neuron found simple linear patterns in historical data. Soon, in your first PyTorch lab, you're going to train that model for yourself. You'll also train on a whole new set of delivery data, and then you'll use your model to make predictions for new customer locations that it has never seen before. This process, using a trained model to make predictions on unseen data, is called inference. But before we jump into the code, we also need to have a systematic approach. So let me show you the framework that we're going to use throughout this entire professional certificate. Whether you're training this delivery predictor or whether you're building image classifiers later on, we're always going to reference this same underlying structure. Here are the 6 stages. Stage 1, data ingestion. It all starts with data. Before you can train any model, you need to gather your raw information and organize it so PyTorch can work with each data point efficiently. For the delivery predictor, that data will come from the company's delivery records. But here's where things get tricky. Maybe earlier records listed delivery times as free text entries like 22 minutes, while newer ones use numeric values like 22.0. And there's always issues with things like missing values, negative delivery times, or records that suggested that you were biking at 200 miles an hour. This kind of messy data is the norm and not the exception. In your first lab, we're going to keep things simple. You'll start with clean delivery data that's ready to use. But understanding these steps now helps you appreciate what goes into real-world projects, and you'll take on more of these challenges yourself as we move forward in the later courses of this certificate. And that brings us to stage 2, data preparation. Getting that data was just the beginning. Whether you're working with delivery records, customer images, or email text, the next challenge is the same. You have to clean, transform, and organize that data into a form that your model can actually learn from. For the delivery data, that might mean things like fixing the errors we spoke about earlier, like removing impossible delivery times or duplicate entries. It could also mean handling missing values when timestamps weren't recorded, or engineering new features by converting addresses like 123 Oak Street into distances like 8.2 miles. This stage often takes the most time and the most code in a real project, and that's normal. Most models don't fail because the math was wrong, they fail because the data was messy. Stage 3, model building. Now that your data is cleaned and is ready, it's time to design the model that's going to learn from it. Now, whether you're predicting delivery times or classifying images or maybe analyzing text, this step is about choosing the right architecture for your problem. Architecture means structure. How many neurons are you going to use? How are they connected? What types of layers does the model need? For your delivery predictor, the architecture is as simple as it gets. One neuron that learns the relationship between distance and delivery time. In PyTorch, defining that model's architecture takes just a single line of code. The beautiful thing about PyTorch is that even this simple model will follow the same patterns as much more complex ones that you're going to be tackling later in this course. And having a good model design is just the blueprint. Next, you actually have to teach it to make those good predictions. And that's stage 4. Training. Here's where your model starts learning. You'll feed in examples like the delivery was 8.2 miles and took 22 minutes, or this one was 12.5 miles and took 31 minutes. And the model will gradually start to figure out the pattern. In the training stage, you'll learn how to configure the key pieces that make this process work. How do you measure prediction errors? How do you guide the model to improve? And how do you control how fast it learns with training settings? Then you'll run the training loop where PyTorch does the heavy lifting and your model learns from the data. But even when training finishes successfully, you're not done yet. Now comes the real test. Can your model make a good prediction on new, unseen data? And that brings us to stage 5, evaluation and debugging. To know if you have a really good model, you need to see how well it performs on new data, and this is examples that it wasn't trained on. To find out, you're going to use a test set. And this is a portion of the delivery data that you held back during training. So maybe a model predicts 28 minutes for a 15-mile delivery, but in reality, it took 32 minutes. How often is your model close? How often is it way off? As you move through the course, you'll learn how to detect deeper issues and debug models when things go wrong. But for now, the key question is simple. Does your model work well enough for you to trust it? Stage 6 is deployment. And this is the final stage. That's getting your model out into the real world for people to use. But let's do ourselves a little favor and we'll leave this one out of the pipeline for now. We'll pop back in when the time comes. Now that you've seen the full picture, you're ready to dive right in. And in the next video, you'll see how even our simple delivery model follows these exact stages in PyTorch code. And then in the lab, you're going to run it yourself and find out whether you should make that delivery. Welcome back. In the previous lab, your delivery company expanded from bike-only service to citywide operations using cars for longer routes. But you discovered something important. As distances increased, delivery times stopped following a straight line. So what happened? Why did your model start to fail when you added cars? Well, it all came down to your model's assumption. A linear model treats every mile as needing the same amount of time, but in reality, it's much more complicated. These first few miles beyond bike range hit dense city traffic, and further out, cars reach highways and move faster. The relationship curves. So what's the solution? You might think, let's just add more neurons. If one neuron learns one relationship, maybe multiple neurons can capture more complexity. But when you have just one neuron, it produces your final prediction, so it is the output layer. But when you add a second neuron, now you have two outputs from your single input, and you need a single prediction in your final output. So you add another neuron to combine these two outputs into one final output. And now those two neurons are considered a hidden layer. These two neurons independently calculate the weighted sum from the input. Let's call their output Z1 and Z2. And your new output neuron takes both of these inputs and combines them into a single prediction. But here's the problem. That's still just a linear equation no matter how many neurons you stack like this. If all operations on a single input are linear, simply multiplying by weights and adding biases, you'll always end up with a straight line. To learn curves and not just straight lines, your model needs something more than a linear transformation. It needs nonlinear activation functions. These functions add just enough complexity to help the model learn more interesting patterns. In PyTorch, we usually apply them element-wise to each neuron in a layer one by one. Let's look at what that means. A neuron starts by computing a linear transformation of its input, something like this. But instead of sending that raw number straight out, we pass it through an activation function like this. And this small change, adding a nonlinear transformation, is what lets your model learn much richer patterns. And now let me introduce you to a really important activation function, ReLU. It's incredibly simple and it's surprisingly powerful. And here's what ReLU does. If the input is negative, output 0. If the input is positive, just pass it through unchanged. It's as simple as that. Don't you just wish that we could ReLU all of those negative things out of our lives? In PyTorch, it takes just one line to add ReLU to your one neuron model. Remember the sequential layer type? That's your assembly line where the data flows through all of those layers in order. Now it goes through the linear layer first and then through ReLU, which transforms the output. But how can something this simple help us model curves? So let's take a look at what happens when you add ReLU to your single neuron. Your neuron will start by computing w times distance plus b. Without ReLU, this will give you a straight line. But with ReLU, when w times distance plus b is negative, the output is 0, which is a flat line. When it's positive, the output follows the line normally. And look at that. You've just escaped the world of straight lines. You now have a bend, a corner where the behavior changes. But here's something crucial. Where does the bend happen? When ReLU is applied to a neuron's output, the bend occurs where wx plus b equals 0, which effectively gives us x equals minus b over w, where it stops outputting 0 and starts responding to the input. Now, think about your city transportation data. The pattern doesn't just bend once, it curves, shifting gradually across different distances as traffic conditions change. So if one neuron gives us one bend, then maybe multiple neurons will give us multiple bends. So let's find out. Each neuron has its own weight and bias, and that means that each neuron activates at a different distance. Picture 3 neurons all receiving the same distance input. Neuron 1 will activate right around 3 miles where the traffic starts. Neuron 2 activates right around 8 miles as we're entering the highways, and neuron 3 activates at around 15 miles when we're at full highway speeds. Now here's what happens. Let's add their outputs together, and their combined output approximates your complex curve. In PyTorch, this entire model takes just a few lines of Python. Let's break that down. But notice we only define 2 linear layers. In PyTorch, you only code the layers that compute. The input is just your data. And ReLU, well, that's an activation function that transforms values and not a separate layer in this count. Your first linear layer is your group of neurons. The 1 means one input feature, and that's the distance. The 3 means 3 neurons, so this layer outputs 3 values. Each of those outputs passes through a ReLU. Then the second linear layer takes those 3 transform values and combines them with a single neuron, producing one final prediction, your delivery time. And if you want to smooth the curve, just increase the number of neurons in your first layer. With enough neurons, each learning where to activate and how strongly to contribute, you can approximate any smooth curve. Your city transportation patterns, with all of their complexity, can finally be modeled. Now, we've been using ReLU because it's the workhorse of modern deep learning. It's fast, it's effective, and it's widely used. But it's not the only activation function out there. Sigmoid, for example, will squash your outputs into a range between 0 and 1, and is great for probabilities. TANH maps your values to a range between -1 and +1, which is really useful for many tasks. And there's lots of others too. If you want to dive deeper, there are a number of great resources such as pytorch.org's documentation and, of course, other deeplearning.ai specializations. But honestly, for most situations, ReLU is all you need. Speaking of what you need, remember that curved city data that stumped your linear model? It's time to go back and conquer it. In the lab, you'll add ReLU to your model, and you'll finally capture those complex traffic patterns. Let's put this knowledge to work. In the last video, you learned how to create, reshape, and debug tensors. Now let's see how PyTorch actually computes with them. Let's start with a computation from your single neuron model, weight times distance plus bias. And here's what that looks like when you have multiple distances to process. PyTorch's tensor math works element-wise, so each element is operated on independently. Your computation applies the same weights to each distance and then adds the same bias to each result. The math looks just like regular Python, but PyTorch runs these operations efficiently on all elements at once. This works for scalars, which are single values, as well as tensors that have the same shape. But what if you have more complex data? Imagine 3 deliveries where each has 3 features: distance, hour, and weather. And now you want to apply adjustment factors, maybe 1.1x for distance, no change for time, and a 5x penalty for bad weather. Creating that tensor with repeated 1.1, 1.0, 5.0 rows works because the tensors have the same shape, but it's redundant. Wouldn't it be nice if you could just specify those adjustment values once? And that's where broadcasting comes in. You know that tensors with the same shape will work element by element, but remember how a scalar could update every value in our distance tensor. When you add a scalar to a tensor, PyTorch automatically expands that single value to match every element, and that's how weight and bias could apply to all of your distances at once. This automatic expansion is broadcasting in action. But what about if we have something like 5? A tensor with a shape of 1, 1. Do you think it will work with our 1, 3 shaped tensor? Well, the first tensor has shape 1, 3, 1 row, 3 values. The second has shape 1, 1, 1 row, 1 value. Normally, PyTorch requires exact dimension matches for operations. Different shapes would cause an error. But here's the magic. When one dimension is 1 and the other is larger, PyTorch will automatically expand the smaller dimension by repeating values. So our size 1, 1 tensor becomes 5, 5, 5, matching the 1, 3 shape. And now they can be added together. Let's look at a more complex example that shows broadcasting's real power. What happens when you combine a 1, 3 tensor with a 3, 1 tensor? Take a moment to think about how this will work. Well, here's what happens. PyTorch looks at each dimension. The first dimension, 1 versus 3, the 1 expands to 3. The second dimension, 3 versus 1, well, guess what? The 1 expands to 3. So both become 3, 3. So how would you actually use this? Well, remember those delivery adjustments? Instead of repeating 1.1, 1.0, 5.0 3 times, you could just write this. No loops, no manual repetition. PyTorch handles it all through broadcasting. And this pattern appears everywhere, adjusting multiple features across batches, combining different dimensions of data, applying transformations efficiently, so many places. Once you know to look for it, you're going to see broadcasting opportunities everywhere in deep learning. Now you've covered essential tensor operations over the last 2 videos. The provided lab has additional examples that you can explore because, like any tool, tensors will become intuitive through practice. But most importantly, you're at the end of Module 1. Congratulations! We started by exploring what makes PyTorch special, and now you've learned the fundamentals. You've worked through the machine learning pipeline, you've trained your first neural network, you've mastered tensor operations. You've built the foundation. Up next is the Tensor Lab, where you'll practice these concepts, followed by a graded assignment to test your skills. Then, in Module 2, you're going to tackle classification problems and dive deeper into how neural networks really learn. You've mastered PyTorch fundamentals. It's time to put them to work. Let's revisit the machine learning pipeline and see how PyTorch handles data. You already know about these steps from Module 1, but now, if you're going to decode Andrew's letter, you're also going to need to understand PyTorch's data handling tools. Before you get into the complexities of image data, let's start with something more familiar, that delivery data that we looked at in Module 1. The same tools that can handle millions of delivery records can also handle millions of images. Once you see the pattern with simple data, images are going to make a lot more sense. So let's imagine your delivery company from Module 1 has grown. Instead of 10 deliveries, you now have 100,000 records to analyze. That's a lot. Now imagine you wanted to try and load all 100,000 records at once. You might use code like this. As you load this data, every piece needs to live in your computer's RAM. With 100,000 records, you might be okay, but what if you had millions of records? Or if you added weather data, traffic patterns, driver info, and all of that kind of stuff? At that scale, your computer can run out of memory and crash in no time. And that's why you need to load your data piece by piece. The practical solution is to work with your data in batches. And these are smaller, manageable chunks of the full data set. But batching is just one part of the picture. Before your data is ready for training, you need to process it, format it, and serve it in a way that your model understands. And that's where 3 of PyTorch's core data utilities come in. And these are transforms, dataset, and data loader. They each handle a key part of the process, and they're designed to work well together. Let's take a look at how transforms work. To apply transforms to data, you usually write something like this. Transforms are operations that run on each data point as it's loaded, preparing your data for the model. Compose just means to do the following things in order. Then you have the 2 most common transforms, toTensor and normalize. Neural networks are surprisingly picky. They train much better when all inputs are small numbers, ideally centered around 0. And that's exactly what these 2 transforms do. toTensor converts your data into PyTorch tensors and scales them to fall between the values of 0 and 1. Normalize adjusts these values even further, centering them around 0 and then scaling using standard deviation. For now, just know that these will help your model train much more effectively, and you'll learn more about them and other transform techniques in the next module. Next up, you're going to wrap your data in a dataset object, which fetches each sample from disk when it's asked to. It doesn't preload everything in one shot, and that's one of the secrets to handling massive datasets. It handles things like where your data lives on disk, how to load a specific sample, how many total samples there are, and of course, how to apply the transforms that you just saw to each sample as it's being loaded. This indicates where you store the data on your computer. Train equals true, well, that lets you choose between training and test sets of data. And if this is new for you, you'll see a lot more about that when I discuss evaluation. And download equals true downloads the data if it's not already there. And you can retrieve a sample from your dataset simply by indexing it. In Module 3, you'll learn how to use the dataset class to build custom datasets. But for now, we'll stick to the pre-built ones that are available in PyTorch. Once you've defined your dataset, you're going to use a data loader to serve the data in batches. It's part of the pipeline that makes training on large datasets possible by requesting one batch at a time from your dataset. Batch size tells the loader how many samples to serve at a time. You can also shuffle the data, which helps the model learn even more effectively during training. Now let's see the complete data pipeline in action. And you're ready to train. This pattern efficiently handles datasets that would otherwise overwhelm your computer's memory. And whether you're working with thousands of delivery records or millions of images, the principle stays the same. Load only what you need when you need it. But getting data into your model is just the beginning. In the next video, you'll tackle the rest of the ML pipeline, and then you'll look at how loss functions and optimizers update your model. I'll see you there. In the last video, you saw how PyTorch helps you manage your data. With tools like Dataset, Transforms, and Data Loader, you can load, prepare, and serve data efficiently, no matter the size of your dataset. Now, let's move on to the rest of the machine learning pipeline. model building, training, and evaluation. In Module 1, you saw sequential in action. And of course, this works great, but there's another pattern that you'll see a lot in PyTorch, creating your model using nn.module. This code does exactly the same thing as the sequential version, just with more control. So let's take a closer look at the structure. Every PyTorch module class has two parts. Init defines your layers, and forward describes how data flows through them. In init, you're just defining what layers exist. It's a little bit like gathering your tools. The actual order comes in forward, and that's where you describe the path that data is going to take through your model. And this is similar to how sequential orders the flow, but written in a different style. And you're going to see this pattern everywhere in PyTorch code. But wait, you've defined this forward method. How do you actually run it? You might think model.forward. But what if I told you that sequential is a subclass of module and it too has a forward method? And how did you run that model? You never actually called forward directly. It's the same for your custom model. Well, when you call the model method and pass the data, PyTorch does more than just run your forward method. It also makes some internal checks, tracks the necessary math, and sets things up for updating the model later. And that's why you always call model passing it the input and not saying model.forward passing it the input. PyTorch will handle that forward call for you, and it's all wrapped up in the essential bookkeeping. So what about this line, super init? Is it really necessary? You might think it's just Python boilerplate and maybe nothing bad happens if you skip it. But when you try to create your model, PyTorch needs to set up a system to track all of its learnable parameters, and these are the weights and biases that you're going to update during training. So when you call super init, it actually creates that tracking system for you. Without it, PyTorch has nowhere to register your layers. So now let's take a look at training. You've seen this training loop already in Module 1. This standard sequence is the core of most PyTorch training loops. Zero grad clears out all the old calculations, backwards figures out the improvements, and step updates your model. But here's the thing, if you don't follow this standard order, your training might fail silently. PyTorch won't throw an error, but your model won't learn properly. For example, what would happen if you swapped backwards and step? Your code runs fine, but the model updates itself based on the previous batch's calculations and not the current ones. Or if you put zero grad after backward, well, then you just threw away all of that work that backward did. What if you put zero grad outside the loop? Well, those calculations just pile up. Each batch will add to the previous one, and your model starts making huge adjustments when it should just make tiny ones. The next two videos will take a deeper dive into these topics. For now, just remember that this pattern is important. You almost always want the same order every time. You've been training your model, but how do you know it's actually learning? That's what evaluation is for. Testing your model on new data that it hasn't previously seen and wasn't trained on. Two critical things here. Model.eval. Be careful. This is not a method that evaluates your model as some people mistakenly think. It just sets the model into evaluation mode. You need this because it's both more efficient computationally and some layers in your model will behave in different ways during training and evaluation. Torch.nograd. This will disable that extra tracking that PyTorch does during training. If you don't turn it off, PyTorch will keep storing lots of details even when they're not needed, and this wastes memory and might even crash your program during validation. Now, the most important part of evaluation is to see how well your model has performed on new data that it hasn't seen before. Testing on the training set would be like giving a student the same test twice. The student might just memorize the answers, but you want to see if they can apply what they've already learned. Since you're exploring image classification in this module, you can easily measure performance using accuracy. The accuracy calculation is straightforward. Count how many times the model gets the classification right and divide that by the total attempts. If your model predicts 9,500 digits correctly out of 10,000, that's 95% accuracy. And don't forget to switch back to training mode if you are returning the model to training. You've now revisited the full pipeline. Data loading, model building, training, and evaluation, but you've only scratched the surface of training. And in the next two videos, we're going to take a closer look at what's happening with loss functions and optimizers. As you move through this professional certificate, you'll see these three lines come up again and again and again during training. They're simple to write, but a lot happens behind the scenes. PyTorch will take care of the complex math for you, but in this video, you'll take a quick look under the hood to understand what each line really does and why the order matters. These three lines will work together in this sequence: measure, diagnose, update. First, you'll measure how wrong your predictions are, and that's your loss, this one number that sums up all of your mistakes. And then, backward diagnoses the problem. It examines how each weight in your model contributed to the error, which weights made things worse, and by how much. Finally, optimizer.step updates the weights. It uses those diagnostic scores to adjust each parameter. The weights with the bigger problems will get bigger corrections. In this video, you're going to focus on the first step, and that's measuring loss. You've already seen one kind of loss function called mean squared error, which works really well for tasks like we had when we were predicting delivery time. You'll also meet a new loss function, cross-entropy loss, and this is used for classification problems. I'll break down how these loss functions work and how to choose the correct one for your task. Every loss function does the same basic job. It compares your model's predictions to the true answers and then gives you a number. The higher the number, the more wrong you are. Back in the delivery company example, you use the model to predict delivery time based on distance. Now, let's say your model makes two predictions. The first prediction, the model predicted 6 minutes, but the actual time was 4. For the second prediction, say it predicted 3 minutes, but the actual time was 5. To figure out how far off you were, you subtract the target from the prediction, and that gives you the error. It's like measuring the distance between your guess and reality. So how wrong was your model overall? Well, loss here is the average error across all of those predictions. Think of it like a report card for your model. The lower the score, the closer your predictions are to reality on average. But if you average out the raw errors, in this case it was +2 and -2, and you divide that by 2 because there's 2 of them, you get 0. It looks like perfect performance, even though both predictions were actually wrong. And this is why you use mean squared error and you square the differences, gets rid of the minus signs. So now both mistakes count and they don't cancel each other out. And that's where that name comes from, mean squared error. And there's one more benefit. Squaring makes bigger mistakes matter more. Being off by 10 minutes is much worse than being off by 1. So MSE loss, mean squared error loss, helps in these two ways. Number one, it makes sure that all mistakes count. And number two, it punishes bigger errors more than it punishes smaller ones. Mean squared error is perfect when you're predicting continuous values, things like distances, temperatures, or prices. But in this module, you're tackling classification. What digit is this? And here you're going to need a different loss function, and we'll use one called cross-entropy loss. With cross-entropy loss, your model isn't just picking an answer, it outputs a confidence score for all possible answers or classes. Take MNIST. Your model must choose between digits 0 through 9. So for each image, it outputs 10 numbers, a probability for each digit. This means I'm 70% sure it's a 3, maybe 8% sure it's a 2, but it could be a 0. And all of those scores should add up to 100%. Now here's the key idea. Cross-entropy loss punishes overconfident wrong answers. If your model says it's 95% sure that this is a 7, but it's actually a 3, that's a big mistake, and the loss will be very high. But if it's only 55% sure it's a 7, it's still wrong, but not as confident, so the loss will be smaller. You want your model to be confident about the right answers and unsure about the wrong ones. Cross-entropy loss helps shape that behavior. Now here's one important warning. Do not mix up your loss functions. Using MSE loss for classification might work, but poorly. Training will be slow and potentially unstable. Are you using cross-entropy loss for regression? It'll probably break because it expects probability distributions and not continuous values. And also, don't compare their raw numbers. My MSE is 0.08, but cross-entropy gives 2.3, which is better. Well, that's just like comparing two completely different things. Same idea, different scale. Just make sure that the number goes down during training. The goal is to minimize loss. So when would you use which loss function? Well, if you're predicting a number, such as temperature, price, or distance, use MSE. And if you're predicting a category, like a digit, animal, or word, use cross-entropy loss. There are lots of other loss functions out there, of course, and each are suited to specific situations. If you're curious, check out the resources below to explore them further. But for now, the great news is that MSE and cross-entropy loss cover a lot of territory in deep learning tasks. So that's the measure part of our sequence. In the next video, you're going to explore how PyTorch diagnoses the problems and makes those updates. I'll see you there. Welcome back. In the last video, you saw how to build the two key components, a data pipeline that loads MNIST images and a neural network architecture that can process them. But if you ran the model right now, you'll just be guessing. In this video, we're going to walk through the code that actually trains that model step by step. Let's start by setting up everything that you need for training. First, device selection. If CUDA is available, you'll use the GPU. Otherwise, PyTorch is going to fall back to the CPU. Then, let's create the model and move it to the device using .toDevice. Remember, both your model and your data need to be on the same device. Otherwise, you'll get an error during training. You're going to be using cross-entropy loss as your loss function, and as you saw earlier, it's designed for classification tasks, where the model will pick one class out of many, and that's perfect for choosing a digit from 0 through 9. And you're using the Atom optimizer with a learning rate of 0.001. You've already seen how Atom adapts its learning rate as it trains by making larger adjustments early when gradients are noisy, and then smaller corrections later as your training stabilizes. So now let's create a function to train our model for one epoch. The function takes in 5 inputs: your model, the data loader, the loss function, the optimizer, and the device that everything should run on. You'll start with model.train, and this puts the model into training mode. You'll set up 3 tracking variables. Running loss accumulates the loss values, correct counts predictions that match the true labels, and total counts all of the samples that you've seen so far. Next, we're going to loop over all of the batches. And in each batch, we're going to move the data and the target to the right device, clear any leftover gradients with optimizer.zeroGrad. We'll then run a forward pass by calling the model and passing it the data to get outputs. We'll compute the loss by calling the loss function. We'll backpropagate with loss.backwards. And then we'll update the weights with optimizer.step. And then you track your progress. Loss.item gives us the label value, and output.max tells us which digit class got the highest score and lets you compare that to that label value. Every 100 batches, you're going to print out the current loss and accuracy. With 60,000 training images and batch size 64, that's about 938 batches per epoch. So you're going to see around 9 updates. Notice what's happening here. Look at the loss number. It's dropping from 0.64 to about 0.17, while your accuracy climbs from about 81% to about 95%, and that's just in a single pass through the training set. And look how little code it took to make all of that happen. But training is only half of the story. You need to test your model on new, unseen data. There are 2 key differences from training. First, model.eval will switch you into evaluation mode. Second, you're going to wrap everything in a with torch.noGrad. During evaluation, you're not training, so you don't need gradients. This will save memory and speed everything up. The evaluation itself is pretty straightforward. You're going to run each batch through the model. You're going to find which class got the highest score with output.max. You're going to count how many predictions match the true labels, and then you can return the accuracy percentage. No optimizer, no loss tracking, no weight updates, just how many did you get right. Now you have your training function and your evaluation function. Let's put them all together. You'll train the model for 10 epochs. That's 10 full passes through the entire training data set. But it's not just repetition. With each pass, the model refines its understanding of what makes a 2 different from a 7. After each training epoch, you're going to evaluate on the test set to see how well it performs on unseen data. This tells you if the model is actually learning generalizable patterns or if it's just memorizing the training data. And here's what you'll see. By epoch 10, you'll notice something really satisfying. The loss is tiny and the accuracy is high. When your accuracy stops improving, it's often a sign that your model is done learning for now, so you may not even need all 10 epochs. And that's it. You're ready to train your first image classifier in PyTorch. Head over to the lab and give it a try. Welcome to Module 3. In the last 2 modules, you've gone from PyTorch fundamentals to building your first image classifier. You can load data, build neural networks, train them, and get real predictions. That foundation is exactly what everything else builds on. But now, things get more interesting. So far, you've worked with clean, well-organized data sets like MNIST, but we're going to be diving deeper into the data side of the pipeline now, because in practice, data sets are often much messier and more challenging. And that's exactly the kind of problem you're about to take on. A botanical garden wants to build a flower identification app for its visitors, and you've been brought in to help. 3 different teams have already tried. They all used exactly the same neural network architecture, identical layers, the same parameters, but they got wildly different results. Why? Because the real challenge isn't just the model, it's also the data. It doesn't matter how sophisticated your model is, if you can't properly access and prepare your data, you're doomed from the start. Bad data handling means bad results, and that's exactly what sank those teams. Now you're taking on the project, and I want to make sure that you don't make the same mistakes, because even the best model in the world can't save you from a broken data pipeline. So let's see what you're going to be working with. The Botanical Garden provided the Oxford 102 flowers dataset for training, and here's what you get when you download and unzip it. A folder full of images, and when you open the folder, they're generically named JPEG files like image0001. And when you open a file, you can see the images inside it are flowers. In many datasets, images are neatly sorted into folders named after their categories, but that's not the case here. Instead, labels are stored separately in a .mat file, which is a compressed binary format from MATLAB, and you'll need to figure out how to extract your labels from this potentially unfamiliar file type. So that's a first glimpse at your data. And remember, the only difference between those failed attempts was how each team handled this dataset. It made all the difference between a successful app and a frustrating failure. So what does handling the data actually mean? Well, when you're working with any data set, there's a natural progression and potential problems at every step. First, you need to access the files and match the images to their labels. With Oxford Flowers, that's already tricky. The images have generic names and the labels are tucked away in .mat files. That's not the most beginner-friendly approach. Next, you need to get the images into the right format, correct size, data type, and structure, so your model can actually learn from them. And then finally, you need to load everything efficiently in batches, not one image at a time, or your training could grind to a really slow halt. Problems can crop up at any of these steps, and they're not always obvious. So in this module, we'll group these issues into 3 categories: access problems, quality problems, and efficiency problems. And when things went wrong for those earlier teams, it could have been any one of those. In this module, we're going to work through each of these problem areas systematically using that Oxford Flowers dataset. Your main tools will be PyTorch's dataset and data loader classes. You've seen them before, but now we're going to dive deeper into what they can really do for you. By the end of this module, you'll have the data pipeline skills to build the Botanical Garden app and tackle any project that comes your way. In the last video, you cleaned up your data with transforms, resizing images, converting them to tensors, and normalizing the values. Now it's time to tackle 2 more essentials. First, we're going to split your data into training, validation, and test sets. And then we'll use Data Loader to batch and serve that data efficiently. But more importantly, you'll see why these steps matter. So let's get started. If more data is a good thing, why don't we just train our model on the full set of flower images? Well, here's the catch. How would you know if your model works on new photos? And that's why you would split your data set. Typically, you split data sets into 3 parts. One for training, one for validation, and one for testing. Each serves a different purpose. The training set is what your model learns from. It sees these images over and over again during training. The validation set helps you check performance during training while you're still tuning things. And the test set is your final check, used only once after training's complete. For Oxford Flowers, you might split that 8,189 images roughly like this: 5,700 for training, 1,200 for validation, and the rest for testing. Let's see how you do that in PyTorch. For the training set, take 70% of the total length of the data, and then 15% for validation. Now you can compute test size as the remainder, and then you'll ensure that the splits add up to the full data set and avoid rounding errors. You'll see output like this. The key is random split. It randomly assigns images to each set, so you don't end up with all daisies in one and all roses in the other. This gives every split a good mix of the 102 flower types. And just to be clear, your original dataset is not modified. You're not slicing it up. You're just creating 3 separate views of the same data. So now you have 3 separate datasets for training, validation, and testing. In these courses, we'll be using a mix of these depending on the main purpose of the lecture. To learn more about how these splits work and why they're important, check out the provided resources or explore the data engineering specialization. Next, you'll use data loader to efficiently load batches from each set. And this is especially important during training for performance. Remember that whole batch size equals 32? That means you'll get 32 samples at a time instead of just one. But here's the interesting part. Looping through a data loader will give you one batch per iteration. I've added a break to stop after the first batch so you can inspect it. Notice that each batch gives you two things: a batch of images and a batch of labels. For example, this means you have 32 images, each with 3 color channels, each size 224 by 224. The label tensor here gives you one label for each image in that batch. That break was a great way to inspect the first batch, but you can also use this pattern. And this is handy for quick debugging without starting a loop. Now we need to add one crucial parameter to our data loaders, and that's shuffle. Why would you shuffle the training data? Well, there's two key reasons. First, if your dataset is ordered, daisies first, then roses, and then sunflowers, your model might learn to associate position with flower type instead of learning the actual features, and that's not helpful for real-world predictions. Second, if the model sees only daisies for many batches and then only roses, it can actually forget what it learned about daisies. Shuffling will mix flower types in each batch, and it will help the model retain everything that it's learning. So why then would we set shuffle equals false for validation and test? Well, that's simple. Your model is not learning from these sets. It's just being evaluated, so shuffling isn't needed, and those problems that we saw earlier wouldn't apply. One more important clarification. Shuffle only affects how data loader serves up the batches. Your original dataset remains unchanged. So now let's clear up a common source of confusion around batches and epochs. Here's the math. You can't have 0.125 of a batch, so you get 179 full batches of 32 images and one partial batch with 4 images. That's the remainder that was left over, for a total of 180 batches. One epoch means you're going through all 180 batches once, seeing every image in your dataset exactly one time. So let's verify this. You can see in this code that you're printing the length of the last 3 batches, and here's the output. Do you see that last batch with only 4 images? Well, that's normal. It's just the leftover images that did not make up a full batch. And this can confuse people sometimes when they expect every batch to be exactly the same size. So when you train for 10 epochs, you're going through all 180 batches 10 times. Your model sees each image 10 times in total, but in a different random order each epoch, thanks to that shuffle equals true. Now let's wrap up this video by looking at 2 common mistakes that can cause major problems as your data loader tries to access samples. And here's one that I see all the time. You can see that I'm loading the entire CSV file from disk into memory every time getItem is called. If your dataset has 5,732 entries, that means that the full CSV, all of those entries, is reloaded every time you retrieve a single sample. So that's 5,732 times per epoch. So if you train for 10 epochs, that's over 57,000 full loads of the same file, which is a massive and unnecessary slowdown. The fix is simple. Load once in init. And here's another common pitfall. If you get CUDA out of memory errors, the first thing to do is to try reducing your batch size. Start with 32 or even 16 and then work your way up to fit available memory. So now let's put everything that we've learned into practice. The output shows everything is working correctly. Proper shapes, correct splits, and efficient loading. You now have a complete data pipeline for the Botanical Garden app, from those messy map files all the way to efficient batch loading. And in the next video, we'll take a quick look at ways that you can bug-proof that pipeline. I'll see you there. In the last video, you explored how convolutional layers work and how CNNs can learn useful filters to extract features and patterns from images. Now we're going to put those pieces together into a full convolutional neural network architecture. And as you can see, it extends nn.module just like you've done before. In the init function, you'll define the structure of your network. It starts with 2 convolutional layers and ends with a fully connected layer to classify your images. Fully connected just means that every neuron in the input is connected to every neuron in the output, and it's just another name for a linear layer. In this first convolutional layer, you're going to start with an image that has 1 channel, so it's a grayscale image. Each pixel has a single brightness value. The model will then try to learn 32 different filters. Each filter is one of these 3x3 grids of numbers, so there's 9 weights per filter. These filters slide over the image and respond to different patterns with a padding of 1. While the output of this layer may look like 32 new images, they're really just arrays of numerical values showing how strongly each filter reacted to different parts of the image. These are commonly known as feature maps or activation maps, and they map where each feature appears in the input. Then comes the ReLU activation, and as you know, it sets any negative numbers in the resulting feature map to 0. And again, this helps the model learn more complex patterns. Then it's fed into something called MaxPool2D. What is that? Well, let's take a look. Pooling is a common technique in convolutional neural networks that's used to reduce the size of feature maps. It's effectively a way to throw away pixels after a filter has been applied, compressing the data while keeping the most important parts in a way that shouldn't affect the results. Let's see this in action. Say you had a kernel size of 2 for the max pool. So on the left, you have a feature map output from a filter. Since your pooling kernel size is 2, you select a 2 by 2 area of values. You'll then only keep the largest value in this group, in this case it's 192, and discard the rest. And that's why it's called max pooling. If you repeat this process across every 2 by 2 group of values in the feature map, you'll end up with a smaller output, keeping only the maximum value from each 2 by 2 area. The logic here is that your filters have already extracted the important features from the original image. So now, by applying pooling, you're compressing each filtered image, keeping just the most significant information. As a result, less data needs to pass through the network, and the next layer sees images that were only a quarter of the original size. And this is important because after your first convolutional layer, you now have 32 different feature maps flowing into the second layer. For large images, this quickly becomes a lot of data. Pooling reduces this volume of information, making your neural network much more efficient without losing valuable details and more robust to small changes. After your convolutional and pooling layers have highlighted and compressed the key features in the image, it's now time to classify the result using a fully connected layer. This fully connected layer combines all of the features into a final prediction. In this example, you can see that the linear layer has 64 times 7 times 7 inputs. The 64 should be relatively clear, as the second convolutional layer has 64 outputs from its 64 filters. But why 7 by 7? Here's a hint. If our nature photos were resized to 28 by 28 pixels for this example, can you figure it all out? Well, remember how the max pooling layer works by taking images from 2 by 2 chunks. So a 28 by 28 image is going to be split in half on each axis, and you'll have 14 by 14 images. The second max pooling layer is going to do the same thing and halve that 14 by 14 to get you to 7 by 7. So then those 7 by 7 feature maps will get fed into the final linear layer. So in other words, each max pooling layer halves the size of its input. Then you have the forward method to define the flow of data, which is pretty straightforward, no pun intended. You pass data through each of the convolutional layers, and then recall that the linear layer expects a single row of values, so you need to flatten your tensor into a single vector and pass it through that final layer to produce a prediction. And that's your full CNN pipeline, from raw pixels to learned features to classification. So far, you've now seen how a CNN processes an image, starting with those learned filters that generate feature maps, and then pooling to reduce the size and improve robustness, and then finally classification through the fully connected layers. So you can now understand the core theory, and in the next video, I'll walk you through the code step by step to build a convolutional neural network using PyTorch.